Okay, so welcome to the second to last lecture. As I noted on Slack, the last class on Wednesday next week will be just an open discussion session on anything you want to talk about among the many topics you've covered. So we've really come a long way in this course, starting from essentially second quantization and the free electron gas, and then talked about um, the effect of electron-electron interactions. Initially, they didn't do much, but then once we got to the Kondo model, we started seeing some remarkable new effects. And then in the SYK model, we saw a complete breakdown of the starting point of the course, which is quasiparticles don't exist anymore, and you get some much more complicated many particle interacting state. And in this last two lectures, I want to talk about a more realistic, but not as well understood theory of a metallic state without quasiparticles, and that's the theory of what I'm calling the critical Fermi surface. So this is a state where the idea of a Fermi surface survives. There's still a Fermi surface. In fact, its location is fixed by Luttinger's theorem. All of that still applies. But there's no pole in the Green's function as you approach the Fermi surface for a quasiparticle. And this kind of state has been observed most famously at half-fill Landau levels in gallium arsenide, and I guess also in graphene. The non-Fermi liquid properties haven't really been studied that carefully because it's rather difficult to extract out from these quantum Hall experiments. Okay, anyway, so but these critical Fermi surveys will be a topic for probably Monday. Today I want to do is actually go back to the very beginning of the course, the idea of Fermi surface, just Fermi liquid theory, but do it a little more systematically in a simplified model. If you remember, when we did Fermi liquid theory, we at one point we said, okay, you get these quasiparticles, the quasiparticles get some mass renormalization, but then they do scatter off each other and have some decay rate. And rather than computing the decay rate honestly for a Fermi liquid, I just computed it using Fermi's golden rule. And there's good reason for that. Fermi's golden rule is a lot easier to apply than to actually do the two-loop calculation that's required. But now today we're going to bite the bullet and actually do the two-loop calculation, but in a simplified model where, as you'll see, actually it's quite doable. It's not that complicated. Nothing more complicated than evaluating one-loop graphs and Lindhardt functions that you've already done, but we'll do it in a slightly different way. Okay, but before I embark on that, are there any questions? Okay, so we're going to start with a discussion of what's called the patch theory of a Fermi liquid. Okay, well, it'll become clear what the approximation. It's not an exact theory, but it's a theory that does really better than any other approach for keeping all of the basic features correct. And then, of course, the reason for using it, of course, is this patch theory that also extend to the case for when you don't have quasiparticles, and there effectively it becomes exact, as we'll argue on Monday. Okay, so we'll start here with the free fermions in any dimensions. Little d is the number of spatial dimensions. This is just free fermion with some dispersion E of k. And as we've learned, these free fermions have a Green's function, which looks like this, I omega n minus ek. So as a function of real frequency, so this is frequency on the imaginary axis. For frequency on the real axis, there's a pole at omega equals ek for all k. So this is just free fermions. and that pole means you have free particles. Okay, so this theory has a Fermi surface where the energy of these poles goes to zero. Ek goes to zero, and then you have a Fermi surface. So there's the Fermi surface, and this is the line Ek equals zero. So we are now imagining I'm in 2 dimensions, but actually for today's discussion will be in any dimension, not except one, of course. The one case is special. Okay, so we are interested in low energy physics. So, and all the low energy excitations are on this line, Ek. Okay, so if I sit at a point on the Fermi surface like this point, then the energy of the electron sitting there doesn't change when I go tangent to the Fermi surface, by definition, because the energy is zero on the Fermi surface. So if I proceed in a tangent direction, the energy to first order and it doesn't change. Okay. On the other hand, to first order, it changes very much in this direction. Okay, so my Ek at this point, if I start at this point, then my Ek I can write as Vf times K perp. A K perp is the momentum in the perp direction. Okay, and I have either sign, it can be negative or positive, and it goes to zero right at this point. So right at that point on the Fermi surface, effectively, I have a fermion that's only moving in one direction. And that's the K perp direction. Furthermore, it's only moving to the right. It does not moving to the left because the group velocity is some number, which is positive on this point. So here, dk, which is the velocity of the particle, is just Vf. If I was at the opposite point, which we'll get to next time, then if I use the same coordinate system, so this direction is still a perp coordinate, then my Ek at this point is minus Vf K perp. So on this side of the Fermi surface, I have a fermion that's moving right along the perp direction. And here I have a fermion that's moving left along the perp direction. So at any given point, I have a fermion moving along one direction. And so that's what's called a one-dimensional chiral fermion. It's chiral because it only moves to the right or the left, depending on where you are. Of course, there's overall parity symmetry because for every point there's right moving fermion, there's some other point on the opposite side of the Fermi surface where there's a left moving fermion. Okay, so this is a 1D chiral fermion. D equals 1 chiral fermion. Okay, so now if I ask you what is the low energy theory of a Fermi liquid, what is, if I want to write on some field theory for the very low energy theory that I can show to my field theorist friends, what is the low energy theory? What are the low energy excitations? Well, from this point of view, you would say, well, actually, I have an infinite number of chiral fermions, one for each point on the Fermi surface. So every point on the Fermi surface, I have a chiral 1D chiral fermion, infinite number of one-dimensional chiral fermion, one for each point on the Fermi surface. And that's my low energy theory. So at this point, you'd be very tempted to say, oh, well, once you have 1D fermions, I can use all kinds of fancy tricks that I learned in 1D, like bosonization that we didn't talk about in this course. But then you can try to bosonize then the theory of this Fermi surface and apply a lot of lessons from 1D. But these are essentially free chiral fermions every point on the Fermi surface. Okay, and if you're interested in basic properties of a Fermi liquid, just very low energy properties that don't involve any kind of lifetime effects, then this is actually an adequate theory. But it's kind of an empty theory because you don't get much for it. There's not much mileage for it. Maybe it simplifies some of the algebra, but why bother? Why don't we just work in the way Landau worked and just think in terms of quasiparticles whose dispersion vanishes on the surface? Yeah, okay, that's my personal opinion. There are many famous people have written many papers on this 1D chiral fermion point of view, but I don't think it buys you very much. But let's just keep going ahead and try to at least write down what I just said in words. And then we're going to improve it. We're going to improve it in a way that well, you'll see. Okay, so how would we implement this in words if I just want a low energy theory for the Fermi surface? Okay, then for each direction n hat, I can be in any direction. So for in 2D, this would just be an angle, theta. But in 3D, this is some direction pointing to a point in the sphere. I'm not assuming the Fermi surface is spherical, but just that there's just one point of the Fermi surface, depending upon which direction you go. You could have Fermi surfaces that are, have all kinds of complicated shapes, and you can generalize it, this formalism, to that too. But let's just imagine that it's some kind of deformed sphere, something like this. Not quite a sphere, but essentially, if you start from the center and you go along any direction, you'll cross the Fermi surface only once and only once. So for each direction, there's one point on the Fermi surface. Okay, so we take the direction n hat, and then there's a Fermi point of the Fermi surface, which we call kf vector. And n hat is, of course, the modulus of kf vector because it points in the same direction. So then we can identify, you can if you give for any given k, we can decompose k along the n hat direction, and then some number we call k perp along. Sorry, something is wrong here. So yeah, we are going still along the n perp. Yeah, so that's correct. That's k perp is exactly what I call k perp. So this is, let's see, let's draw it over here. So you start from this point, and you're going to go to that point. That's my k. This is my n hat pointing towards k. So, and this point is kf of n hat. And this distance here is what I'm calling k perp. Okay. All right. So that for every point, there's a unique, every k, there's a unique point on the Fermi surface that is related to, and it's a distance k perp from that Fermi surface. Okay, so now we assume that this k perp is small. Since we're near the Fermi surface, we don't care about points away. And so we're going to write our electron at momentum k as a field which has a label, and it's labeled by points on the Fermi surface. And the momentum is just measured by the value of k perp. So once I give you the value of n hat and k perp, I know what k is. It's just equal to this. And kf of n hat is a known function because I know the shape of the Fermi surface. So I make this, rewrite it this way. And then I just expand the momentum, the energy dispersion, and the energy dispersion will be just this VF k perp. And then when I go to real space, that becomes d by d x perp. So when I'm done, this is my theory of a Fermi liquid. I have a fermion, which is only a function of one spatial coordinate, x perp. but it's labeled. This is just a fixed label once and for all by a point on the Fermi surface. It's not a dynamic degree of freedom. It's just another label like spin or isospin or any other label an electron may have. It's not a coordinate. And there's an infinite number of values for n hat for every point on the sphere. So I have to integrate over the points on the sphere. And for each n hat, I have a theory of a 1D chiral fermion. This is just a, in fact, if I was writing down the Dirac equation in 1+1 dimension, I'd have a left moving and a right moving fermion. So this is half of a Dirac fermion, sometimes called a wild fermion, I guess. So it's just a fermion that just moves along the n hat direction, basically. Okay, so that's the theory of a low energy theory Fermi liquid, plus their interactions associated with the Landau parameters and so on. Okay. However, we know that ultimately Fermi liquid is very different from a 1D electron gas. It's really not a Lagrange liquid. Once you put in interactions, the effective interactions are much weaker in 2D than in 1D. The 1D that leads to a very different theory with, you know, in which in the end the electron quasiparticle breaks down, but there is a new bosonic quasiparticle that emerges. But here we have an infinite set of these chiral fermions, and they all interact with each other. And that interaction Landau taught us, and which we of course showed earlier in the course, doesn't lead to breakdown of quasiparticles, but to normalize the dispersion and also introduces some Hartree interaction between the electron densities at different points on the Fermi surface. Okay, so that's a perfectly adequate theory for that purpose. But suppose I want to compute the lifetime. I want a theory that even has some lifetime, some scattering of quasiparticles. This theory won't do it, and I'll show you the theory that does. Well, and it's in general it's a difficult problem because for the following issue. That's why I didn't do the calculation honestly, because it's a very complicated integral that you have to do. So if here's my Fermi surface with some shape, and then I take a particle that's somewhere over here, and I ask what's the decay rate of that particle. Now that particle is very close to the Fermi surface, so the best it can do is move from there to some other point on the Fermi surface, which is even closer. So this is point 1 to 2. But the point is that even though it has a very low energy, there's a lot of space for it to scatter with very large momentum. So that's really the complicated thing about a Fermi surface. Low energy does not imply low momentum. So this is something, for a particle theorist, this is the hardest thing to get accustomed to. Because in particle physics, energy and momentum are, with low energy goes low momentum. So you never have to worry about this. But here you could have a process in which there's a very large momentum transfer, but very low energy. And at the same time, while it's doing this, you can take another particle even all the way here, sitting here, put that in green or something. And that particle will have to go to an empty state over here. And you just have to make sure that energy is conserved and momentum is conserved. And I try to at least draw the energy, the momentum conservation, make that clear, because this momentum is equal and opposite to that momentum. So in fact, total momentum is conserved. And that's a very large momentum that's transferred. So this is the kind of processes we have to consider. It could scatter all the way here, whereas the other one scattered this way. There's a lot of large momentum processes which have very, very low energy, and we have to account for all of those to figure out the lifetime of a quasiparticle. And that's not easy. You have to write down the whole equation and just, try to evaluate that usually on a computer. So what I'm going to do is I say, okay, this is preparing for the breakdown of quasiparticles. As we'll see, that to break quasiparticles down, these large momentum processes are really no use. They give you some scattering, but the scattering rate is relatively small, and they don't lead to breakdown of quasiparticles. To have breakdown of quasiparticles, generally you need small momentum transfer and small energy transfer. Now there's a caveat to that. Sometimes you have autoparameters like antiferromagnetism that have some wave vector like pi pi. But even there, you fix pi pi, and then you have momenta that has to be close to pi pi to any breakdown of quasiparticles. But I won't talk about those type of things. Okay, so what I'm going to do now, just to make life simple, in a Fermi liquid, I'm going to assume that small energy implies small momentum. So what that means is that I'm only going to consider processes like this, where an electron scatters from here to there, and another electron scatters from here to there, or something like that, conserving energy. It's all happening near the Fermi surface, near the same point that you started with. That's an assumption, and under certain circumstances, those processes become very strong, and those are exactly what we'll talk about on Monday. But for now, let's imagine that we're just making life simple, and we just take some very simple interaction for fermions near some point on the Fermi surface. Okay. All right, so this is what we're going to do. So we're going to pick a point on the Fermi surface, call it K naught. And we're just going to focus on phenomena near K naught, at least for today. So we just focus on anything that's happening here. And you can notice from the picture, the Fermi surface, I'm also going to worry about the fact that the Fermi surface is not flat. It has some curvature. So I picked the point K naught and I defined my axes so that X is perpendicular to the Fermi surface and Y is tangent to the Fermi surface. Y could be, if I was in 3 dimensions, Y is a 2-dimensional coordinate. If I'm in 2 dimensions, Y is a 1-dimensional coordinate. X is always a 1-dimensional coordinate. And now in the old tangent theory, when I was doing the tangent theory here, this theory, the Fermi surface was essentially flat, was independent of Y. So in the tangent theory, we took a straight Fermi surface here. And we just approximated the Fermi surface by a series of tangents. But as long as I was a given point and had nothing dependent on Y, it only depends on X. But now I'm going to sit at this point and also allow for the Y dependence. So you can just see from this shape here that the energy will change linearly in this direction, but it changes quadratically in that direction. And you're tangent to the Fermi surface, so there's no change to first order. But that quadratic order, there is some change. And it's that quadratic change that gives you this parabolic shape at this point. Okay, so let's expand EK about that point. So my EK, is even if I suppose my energy was EK was, let me give you an example, was just K squared over 2m. Let's just take it, even for a spherical Fermi surface, this happens, but you can work with any shape. And so there's a chemical potential, which I call Kf squared over 2m. So now I take my K to be Kf plus Kx. So I take the point, this is the point x0 and Ky. So now I expand this out, what will I get? I get Ek is Kf plus Kx squared over 2m plus Ky squared over 2m minus kf squared over 2m. And that, if I keep only the leading term in each direction, I'm going to get kf over m times kx plus ky squared over 2m. So there you see, if this is point k0 now, k0 I took to be kf 0 in this coordinate system. So now I see that along the x direction, there's a linear dispersion, it's vf times kx, whereas along the y direction, it's a quadratic dispersion. And what's the equation of the Fermi surface? The equation of the Fermi surface is Ek equals 0, of course. And in this approximation, that's the equation of a parabola, not a circle. That tells me that kx is minus m over kf times ky squared over 2m. And that's exactly the equation of this line here. So at least for a spherical Fermi surface, the m parameter plays two roles. One, it determines the Fermi velocity as kf over m. And two, it's on its own, it determines the curvature along the y direction. Now, of course, if you had a more complicated shape, these two numbers are independent. So in the end, the dispersion, so this is how I'm writing it in general. So I'm now saying that Ek will be just Vf times Kx plus kappa over 2 times Ky squared. So I have two parameters, Vf and kappa, representing the curvature and the Fermi velocity. And we do have to keep track of kappa to understand quasi-particle scattering. Put kappa equals in 0, which is what the chiral fermion model was, the 1D chiral fermion. Then you get nonsensical answers when you try to compute anything involving scattering. Okay, so having done that, then I can write down my low energy theory. So now this is a theory not of infinite number of 1D chiral fermions. It's in fact a theory of just one fermion with, okay, I give it some spin label A, which is living in D dimensions. But it's not anything that it has a very peculiar dispersion that you wouldn't meet in relativistic field theory. Its dispersion looks like this. It's linear in one direction and quadratic in the other. And most importantly, which is something you definitely don't meet in field theory, if you ask at what momentum is the energy zero, energy of excitation zero. Now, if you had a massless Dirac fermion or a Weil fermion, anything relativistic, some massless particle, or like a photon, you ask at what momentum is the energy zero? The answer is a point in momentum space, which in field theory is just k equals 0, or if you're talking about graphene, which is also has massless Dirac fermions, it's some wave vector you call k, but it's still a point in momentum space where the energy goes to 0. But here, if I ask the question, at what energy is this 0? The answer is it's a surface in momentum space. In 2 dimensions, it's a line. In 3 dimensions, it's a 2-dimensional surface where the energy goes to 0. So that's why this is a very, from a field theory point of view, kind of a sick theory. It's got many more low energy excitations, in fact, 0 energy excitations that you would than you would expect. Okay. All right, so this is, I spent the entire first half hour just talking about free fermions, different ways of writing free fermions. All right, so now let's put in some interactions. So we're going to put in, where did it go? We're going to work in the long wavelength limit. Where are the interactions? Here. So this is our interaction. we're just going to work, it's in the vicinity of the point K naught, and we just put in a Hubbard-like interaction. Let's not, these are the spin labels or something. So basically it's N up and down if these are up and down. And so this is just a contact interaction between these fermions. All right, so what we're going to do is now actually do some computations of a two-loop graph in this very simple theory. And it's not so bad. Okay, show you it's not so bad. So we're going to compute the self-energy of the electron, honestly, where EK is just this dispersion I've been telling you about. So we're going to compute sigma. There's some Hartree terms, first order terms, which we have thought about, but we won't worry about those because they all just give you real contribution to self-energy, and they're reabsorbed into the definition of EK. So we're just taking all of that. So we're really interested in terms that have a frequency dependence, or a interesting temperature dependence at low temperatures. What we learned from Fermi's golden rule, that the frequency or temperature dependence for K on the Fermi surface, in this case, that's Kx equals Ky equals, when Ek equals 0 is a line passing through the origin of coordinates. And so on the Fermi surface, sigma should be omega squared or temperature squared. That's what Fermi's golden rule tells us. But let's do an honest calculation of sigma. Okay, so the graph that we're going to evaluate is this one, and basically this is the only one you can see for that model. So this is the graph, the two-loop graph, but this is the interaction U naught. There's a U naught here, a U naught there, and these are electron Green's functions. So I've deliberately drawn it this way to make something evident. And what I want to make evident is that there's this bubble here, which is exactly the Lindhardt function that we have spent so much time on. That was the density correlation function of polarizability that we computed very carefully. So that's a subgraph. So assume I know this subgraph and I call it pi, then I can divide up computation of this Feynman diagram to two steps. First, you compute the subgraph, and then you put it into the next graph and compute the self-energy. So this is written down here in steps. So this is the polarizability. It's G naught times G naught. This is the kind of thing we have computed before in great detail. I spent, I think, probably a lecture and a half showing what it might look like in different regimes of frequency and momentum. And then once I know pi, which is this graph, then the full self-energy will be pi times another electron Green's function. And that's over here. So first I have to compute pi, and then I have to compute sigma. Okay, so let's start with pi. So what I'm going to do now is try to compute pi in a much easier way. I spent a whole lecture and a half computing before. We did the frequency summation and got this Lindhardt function, and then we had to do all kinds of fancy tricks with momentum integration to figure out what's going on. But here, so if I look at what am I going to try to do? So if I look at, just to remind you, this is something we talked about. This is Q, going from 0 to 2, to KF, something like this. There's no need to draw that line. Then we had this particle hole continuum that hopefully you remember, where in this region, we had M pi of omega Q not equal to 0. So these were the where we had particle hole excitations with energy omega and momentum Q. This direction is omega. So here I've said I'm only interested in very low momenta. So my attention now is going to focus on just down here. Okay, and you may or may not remember, it's okay if you don't, because you're going to derive this result again, that in general D dimensions 2 and above, in this region, the imaginary part of omega over Q, omega and Q, was omega divided by Q times some number, which we are going to compute now. Okay, so this is the very low momentum, low frequency, low energy part. And this picture also illustrates what I was just saying. If I'm interested in very low frequencies, which I am, there's no that I can justify at low energies because my quasi-particle is right near the Fermi surface. If I'm interested in very low frequencies, that means I'm interested in somewhere down here. I can have both high momentum processes up to 2 kF and low momentum processes. But I've just by fiat said I'm only interested in this part. Okay. So if I'm only interested in this part, then actually I don't have to go through all that laborious song and dance I went through to compute pi very accurately everywhere. I can just compute it actually very quickly and to a remarkable and get actually the correct answer for certain contributions. And those contributions are the ones that are important at low energies, which is the imaginary part of pi at small q. So that also has a non-analytic, you can see this very non-analytic dependence on Q, and that is what I'm interested in. So if I'm only interested in the imaginary parts or non-analytic momentum dependence, then I can play a few tricks with the Feynman graph and simplify my life enormously. Okay, so that's, and the reason I'm showing you these tricks here, because these same tricks we're going to apply over and over again next time for the non-Fermi liquid. But in this case, if you don't believe the tricks, you can go back and check with the more complete calculation that the tricks are fine. So might as well learn them here, where you're going to they're going to be very useful later on. And here you have sanity checks to make sure what you're doing makes sense. Okay, in fact, I'm going to go ahead and evaluate this pi. And I'm even going to replace the G naught, which is the bare Green's function, by a fully renormalized Green's function. I'm going to cross out the zero. Why? Because the tricks turn out to work even without the zero. You can take a full Green's function, meaning that in this graph, in this G over here, I can have further subgraphs like this, just like in the SYK model. I can have all of these things, interactions within interactions within interactions. All of these are included just by replacing that G by a G naught by a full G. Okay. And as we'll see, when we take this contribution, the self energy is not a function of K and omega. It's just only a function of omega at small k for the low energy contribution. So let's assume that's also the case, and that will turn out to be self-consistent. All right, so finally, I have a graph integral that I need to evaluate. So let me write down the integral. So it's this thing. Yeah, so the integral I need to evaluate for pi okay, I'm going to have a very complicated expression, k plus q. So it'll be, remember, the I epsilon n plus I omega n minus Vf times kx plus qx minus kappa over 2 times ky plus qy squared. And then I have the self energy sigma of epsilon n plus omega n. And then the g of k, which will be I epsilon n minus vf times kx minus kappa over 2 times ky squared minus sigma of epsilon n. Okay, that looks perfectly horrible. How could I possibly evaluate that? Now, what we did when we computed the Lindhard function, what we did was we ignored the self-energy, first of all, and then we did the frequency summation. And then we got the Lindhard function. And then we had to do a very complicated momentum integral. What we're going to do now is to reverse the orders of things. And I'm going to reverse the orders of things because you can see life is very complicated for many things here, but it's extremely simple as a function of kx. There's a linear function of kx here, and there's a linear function of kx here. So basically, as far as kx is concerned, I just have an integral dkx over 1 over kx plus some number and kx plus another number. And those types of integrals I know how to do. The way you do them is just by the method of residues. You find the poles of each of these and you just get the answer. Okay. You close the contour either in the upper half plane or the lower half plane. Okay. So you can immediately do the kx integral. There's just one thing you have to know. You have to know something about the imaginary part of sigma, just to know whether the poles are in the upper half plane or the lower half plane when I'm doing this integral. These are just complex numbers. And so what we'll see in the end, and really is required by the self-consistency of the whole procedure, is that the sign of the imaginary part of sigma is the same as the sign of its argument. In other words, if I look at the imaginary part of sigma, whether it's positive or negative, it's the same as this, whether this thing is positive or negative. So that life simplifies life enormously. I can just absorb the sigma into this as far as deciding whether the pole is in the upper half plane or the lower half plane. Okay, so then I just do the kx integral by the method of residues. Okay, and then first thing I see that in fact, for a large number of values, this is just 0. And the reason it's 0 is it can be 0 is if this object here has the same sign as this object. Because if they have the same sign, then suppose they're both positive and imaginary, then the pole is in the upper half plane of kx, because kx is vf times this, and this divided by vf. And it's also in the upper half plane here. So then I can just close the contour in the lower half plane. I mean, this is just, if these are both imaginary numbers and they are both in the same half plane, then this integral is 0. Okay. So the only way the integral is non-zero is if these two terms have opposite signs. And then you can do the integration. So then you carefully work that out, and you get an expression like this, where you get the difference of the poles, and then the numerator demands that the frequencies have opposite signs. So that's already really nice. And now if you look at this, now you see that you can also make progress in the y direction. So along the y direction, there's a term linear in qy, and there's a term that got some curvature in it. Well, they both depend on kappa. This term wouldn't be there, but this is, so let's assume that again, qy is small and so on. So we throw this term out. And so now as a function of y, I can, so q fixes a direction. So I pick the direction of ky along qy. That's the direction I'm going to integrate. So ky is going to be parallel to qy, and the transverse directions I won't be able to integrate. But they don't exist in higher than 2 dimensions. So then this whole integral is basically of the form, if I just take the direction qy, they're basically ky plus a, ia, integral dky, where I is some number. Well, what is that equal to? Well, so that integral is not really well defined. But if I'm only interested in the imaginary part, it's perfectly sensible. It's just equal to dky times ky minus ia over ky squared plus a squared. And now, if you assume that it's symmetric about y is positive and negative, which it really isn't ultimately, the real part will be 0. And the imaginary part, you can do the integral. It's I times pi. You get an a here, and you get an a here, it'll cancel out. And the only thing, so you get a over mod a, so the only thing that will be left over is the sign. So that's quite remarkable. When you do everything, everything's dropped out. The only thing that you care about, as far as this whole object is concerned, is the sign of this object, which is the same as the sign of epsilon n or something like that. Yeah. Okay, so and now you have this free integral. So this integral, you don't know what to do. You say, well, it's just some cutoffs. But in 2 dimensions, this doesn't even exist. So let's just focus on 2D. There's no such integral left. And now I can do the summation over epsilon, because this thing is mostly 0. It's just a finite summation. And there's my answer. So this I just approximate by some cutoff. So there it is. So now I have got this mod omega over q term that I told you about. It's real for imaginary frequencies, but when you analytically continue, it'll become positive, imaginary, and exactly of this form. And in 2 dimensions, I've got exactly the right coefficient. So you can go back and check, which I haven't, that this is exactly the right coefficient. And amazingly, the sigma just completely dropped off. Didn't matter what it is. There's something universal about the low frequency contribution to the particle hole continuum, sometimes called the Landau damping term. It doesn't depend on anything except the Fermi velocity and the curvature of the Fermi surface. All right, so now you continue playing that. So now, of course, there were a bunch of funny stuff here where I just assumed this was 0 and made a small ky approximation. I had to put a cutoff. Okay, so, but at least in 2D, this was fine. And this is, of course, even at small momentum, this is not the full answer. There's also the real part of it, just the compressibility, the density of states. You're not going to get that by this, because that's not a non-analytic contribution. And the analytic terms, you have to honestly do it the way we did it the old-fashioned way. But if you're interested in the singular terms and the imaginary part, then actually these integrals are quite easy to evaluate. Okay, so that's quite that sink in. Yet this really complicated integral to evaluate, and a d plus 1 dimension integral at 0 temperature. Well, it all simplifies. If you only want to pull out this non-analytic term, it all depends upon which order you integrate things. And if you integrate at this order, then you get the result in fact is even independent of sigma, which you don't know. Okay, so that's really beautiful, and it's this trick we're going to apply over and over again. All right, so now proceeding in the same way, you put this mod omega over qy here, and now you apply the same trick to this expression. So pi becomes mod omega over q. You know what's g naught. You plug that in here and play the same tricks. Okay, so now what happens? Right, so this, what's going on here? Okay, I have gone a bit too fast. But let's see, where's the mod omega over Q? Yeah, there's the mod omega, mod epsilon over Q, because I had a pi of Q and epsilon, I presume. Yeah, so this thing gives me yeah, this divided by that. Oh, the other thing which I didn't emphasize, when you do this integral, what appears here is Qy, not the full Q, it's Qy. The y component of Q is what appears here. And you can say, well, no, actually, initially I had the full Q there. So when I did the calculation months ago. And how do you answer that? Well, the point is that for any given Q, this contribution to pi of Q and omega will come from the point of the Fermi surface, which is tangent to the Q. So if I go back here, if I had the full Fermi surface, and I wanted to compute pi of Q and omega along this direction, but if I want to compute pi of Q and omega along this direction, I have to do the computation along this patch here, where that's the tangent direction. And so for any given direction of Q, there'll be in fact, 2 points in the Fermi surface where I'm tangent to it. And that's the part that gives you this non-analytic term. You can go back and look at the full computation and see that's exactly what happens. All right, so you had a Qy here, but now we are still at the same point. We're at that point, and this depends only on Qy. And that enormously simplifies life in this integral, because this only depends on Qy. And so there's no dependence when I'm doing the integral over Q on Qx. The only dependent on Qx is here. There's nothing here. So I can just do the integral over Qx. And that's very simple because the dispersion is linear. And I just get exactly this type of integral again, but along the x direction. And so when you do that, this is what you get. So this is just some number given by a cutoff. And this is in summation you can evaluate, literally evaluate it, and this is what you get. So there's your omega squared and t squared dependence and there's an I out front in the imaginary part of the self energy. Okay, so that's as honest I'm going to get in computing the lifetime of a quasi-particle. And I mean, for fun, if you want to see where this came from, and how did I get from here to here, that comes from actually just using sum over integers. So you have to just decide. Okay, it's a fun mathematical exercise, but what I'm using there, so if you look at this object here, sine epsilon n plus omega n, so as a function of epsilon n, this thing, it changes sign. Well, it's okay. There's lots and lots of cancellations here. So let's see. So this object is epsilon n. So we plot epsilon n. So this is epsilon n. And I plotted mod epsilon n. And then I multiplied by sine epsilon n plus omega n. So if omega n is somewhere over here, it's going to change sign there. So the actual curve that I'm summing over, the function I'm summing over is this function. Oops. This curve here, here, and then it flips sign and goes down there. So you can see that this portion will exactly cancel that portion. I only have to sum over here. So I have to discrete sum epsilon n over here, and I have to sum over n over some up to some value, and sum over n of n is equal to 1 to n. Well, that is n into n plus 1 over 2. So you use that result, and then you convert all the frequencies back and forth, and believe me, and I checked, you'll get this result. So you can even do the summation at finite temperature, or you can just do the integral So that's what this thing is. It's just equal to this for any and temperature. You just, okay. And if you now analytically continue, the omega squared will become minus omega squared when they go to real frequencies. This will, of course, remain the same. So in the end, you get omega squared plus pi squared t squared is the imaginary part of the self-energy, times some number, which is about a u naught squared. And at least in 2 dimensions, we have an accurate estimate even of the prefactor. Okay. So that's a rederivation then, that the lifetime of a quasi-particle becomes very long. Divergence is 1 over temperature squared as I approach the Fermi surface. And I've just derived that in this kind of long wavelength theory. And for the first time in this course, semi-honestly evaluated a 2-loop graph. And of course, I judiciously chose this graph because it's the simplest. But remarkably, when I go to the last lecture on the non-Fermi liquid, the integrals won't be any more complicated. It'll be very similar to what we've done. Just presented this in a way that everything was going to start looking very simple when we get to breakdown of quasi-particles. And believe me, the original papers on the breakdown of quasi-particles by well, a whole bunch of people were just totally incomprehensible to me. I couldn't understand. They were all written in some very complicated graphs, which I thought only super people could evaluate. I couldn't figure that out. But eventually, this simple method became clear, and actually Max Mitlitsky, my former student, played a big role in clarifying all of this. And now it's just, once you've used these tricks, it's really very simple. Hopefully, I've shown you that. All right, any questions?
I have a question.
Yes, Maria.
Yeah, so what is the advantage of this approach compared to just normal Landau from liquid theory, where you just write down quasi-particles and?
Well, it has advantages and disadvantages. The disadvantage is that we're not accounting for contribution to self-energy from high momentum processes, like this process here, like this is a high momentum process. We're not accounting for that. We're only accounting for processes like this. Or another way to put it, we're only accounting for, in the particle hole continuum, we're only accounting for this damping of quasi-particles due to particle hole excitation in this region. We're not accounting for them at this region. These are all low energy regions. We're just throwing these out. Okay, now if you want to account for all, there's no choice but doing these integrals, evaluating these graphs completely. And that's not at all easy to do it on a computer. I don't think anyone's ever done them analytically. People only have some estimates here and there to make sure that it goes as t squared. That's about it. That's not easy at all. So if you want the full answer, the full lifetime of a quasi-particle, it's first of all, lifetime of a quasi-particle is really beyond Landau-Fermi liquid theory. It's not part of Landau-Fermi liquid theory. In Landau-Fermi liquid theory, the lifetime is infinite. So you're looking at corrections to Landau-Fermi liquid theory. So if you want the correction from all possible low energy processes, well, there's no choice but doing the hard calculation. But if you're satisfied with the correction to Landau-Fermi liquid theory from long distance processes, small q, then this is by far the easiest way to do it. This is the way you do it. So it's just a way of computing the corrections to from Landau-Fermi liquid theory in the simplest possible context.
Yeah,
and the reason I'm doing it. Go ahead, Maria.
I don't know. Go ahead.
Yeah, the reason I'm doing this is, so for Landau-Fermi liquid theory, just focusing on the long wavelength processes is not justified, because we should only focus on the low energy processes. But but in a Landau Fermi liquid, low energy does not imply long wavelength. It can have large wavelengths. But once we get to a non-Fermi liquid, which is on Monday, once we get to critical Fermi surfaces where the quasi-particle breaks down, the total breakdown of Landau Fermi liquid theory, not correction to Landau Fermi theory, but a breakdown of Landau Fermi liquid theory, is in fact occurs due to long wavelength and low energy processes. You need both. So, and we are preparing for that. So that's why. So even though if I just want a correction to Landau Fermi liquid theory, focusing on long wavelengths is not justified. It will be justified when I consider a system where Landau Fermi liquid theory breaks down.
I see. Yeah, that makes sense. And another thing is when we change a shape of the Fermi surface, even just a little bit, the theory will be very different, right? If, for example, in X direction, it's a little longer than in Y direction, something like this.
Well, the calculation will be very similar, except the values of VF and kappa would change. That's all. So for any point on this Fermi surface, you have some value of VF and you have some value of kappa. And depending on which point you're looking at, for the self-energy of the quasi-particle, you'll get different values of VF and kappa. But other than that, there won't be any change.
I see. Thanks.
I have a quick question about the integral for self-energy.
Yeah.
Like, are we always allowed to exchange the frequency summation and momentum integration order? Or there's some property?
Depends what you want to know. So if you are, roughly speaking, if you're interested in the full value of the integral, including contributions from high energies and high momentum, then you have to do it in a certain order because, well, if you kept the full dispersion, if you kept the full E of k at all k, not just the linearized portion near the Fermi surface, then it doesn't matter. You're allowed to do it any order. But now that we're linearizing the dispersion, then there are certain UV divergent terms here. We saw a little bit of the UV divergence right here, but only above 2 dimensions. But we're not interested in those UV divergent terms. We're only interested in the terms that are non-singular. And so if you're only interested in the non-singular, the terms that are singular, excuse me, like things that depend on 1 over Q or something like that. And you want the imaginary part only, because the imaginary part automatically will only be dominated by the IR low energy excitation, not the high energy excitations. So if you want the imaginary part, the singular part and the imaginary part, then you're allowed to freely exchange, because nothing should matter because you're only dealing with the infrared part that is just quite universal, and you don't care about the UV because the UV doesn't give you a singular contribution.
Yeah, so it's equivalent to like extracting the non-analytic part.
Correct. Yeah, this is the non-analytic part.
Mm-hmm. Yeah, thank you.
And if you're interested in the non-analytic part, it doesn't care about UV divergences, and therefore you can evaluate things in any order you want. And definitely the easier order is to do the momentum integration first rather than frequency integration for all of these things today and on Monday.
Yeah, thank you.
Sure. Okay, so that's probably more about Fermi liquid theory than you ever wanted to know, but it's preparing us to now destroy the Fermi liquid on Monday. All right, okay, see you on Monday, and maybe tomorrow discussion session at